In Chapter 14, some biological rhythms are longer or shorter than a day. It defines infradian as referring to a rhythmic biological event whose period is longer than that of a circadian rhythm, that is longer than a day. For example, the 28-day human menstrual cycle. Animals are also characterized by annual rhythms. Most animals only breed during specific seasons. These rhythms are sometimes driven by exogenous factors such as food availability and temperature. In the lab, seasonal animals exposed to short days and long nights, mimicking winter, will often change to the non-breeding condition. Annual rhythms such as body weight persistent under constant condition in the lab and with circadian rhythms in constant light. Seasonal animals in isolation show free-running annual rhythms of a period not equal to 365 days. Circannual is defined as occurring on a roughly annual basis. SNN lesions disrupted circadian activity cycles, but in some animals these lesions did not affect circannual changes in body weight and reproductive status. Circannual cycles do not come from the circadian clock but seem to involve a mechanism separate from the SCN. Light cycles are a measure of day length. They can affect how long the nightly amount of melatonin secretion lasts for. Ultradian is referring to a rhythmic biological event whose period is shorter than that of a circadian rhythm, usually from several minutes to several hours long. For example, activity, feeding, and hormone release. Ultradian rhythms may be superimposed on a circadian rhythm and in performance on various boring tasks reflect fluctuations. In Sleeping and Waking, it says that sleep that starts from late in the evening to early in the morning is the most obvious circadian rhythm. The beginning and end of sleep are synchronized to external events, such as light and dark. People in constant conditions free run, indicating that we too have endogenous circadian clocks. External cues such as lights, meals, jobs, and alarm clocks make our clock a 24-hour period, and this encourages our circadian clock to sleep at some times of the day and remain awake during others. In humans, sleep exhibits different stages. Electroencephalography, or an EEG, is a recording and study of gross electrical activity of the brain recorded from large scalp electrodes placed in the scalp. It provides a way to define, describe, and classify levels of arousal and state of sleep. Electrooculography, or EOG, is the electrical recording of eye movements. Electromyography, or an EMG, is the electrical recording of muscle activity. Electrophysiological measurement led to the discovery that there are two classes of sleep. The first being a rapid eye movement sleep, or REM sleep, and it's also called a paradoxical sleep. A stage of sleep characterized by small amplitude, fast EEG waves, no postural tension, and rapid eye movements. Non-REM, NREM sleep, is a stage of sleep without rapid eye movements. In humans, this is divided into stages 1, 2, and 3 sleep. In stage 1 sleep, or NREM1, the initial stage of NREM sleep, which is characterized by small amplitude EEG waves of irregular frequency, slow heart rate, and reduced muscle tension. Stage 2 sleep, or NREM2, a stage of NREM sleep that is defined by bursts of regular 14 to 18 Hz EEG waves called sleep spindles. Stage 3 sleep, or NREM3, is a stage of NREM sleep that is defined by the presence of large amplitude, very small waves, delta waves. Beta activity, or desynchronized EEG, is an EEG activity seen in wakefulness, comprising a mix of many different high frequencies with low amplitude. Alpha rhythm is a brain potential of 8 to 12 Hz that occurs during relaxed wakefulness. The vertex spite is a sharp wave EEG pattern that is seen during stage 1 slow wave sleep. It happens as drowsiness sets in and the time spent in alpha rhythm decreases. Sleep spindles are a characteristic 14 to 18 Hz wave in the EEG of a person in stage 2 sleep. K complexes are a sharp negative EEG potential that is seen in stage 2 sleep. Delta waves are the slowest type of EEG wave, about 1 Hz, and is characteristic of stage 3 sleep. Slow wave sleep, SWS, also called NREM3, a stage of NREM sleep characterized by large amplitude delta waves. In humans, this is also called stage 3 sleep. Scalp recordings after 90 minutes, the time usually required for progression through these stages, display a pattern of small amplitude, high frequency activity similar in ways to the pattern of an awake individual, even though the skeletal muscles are completely relaxed and limp. This is typical of REM sleep. The flaccid muscle state appears despite intense brain activity because during this stage of sleep, brainstem regions are profoundly inhibiting motor neurons. This is why it's called a paradoxical sleep. Breathing and pulse rates become irregular, as well as the rapid eye movements during REM sleep, and experience vivid dreams. EEG activity shows that sleep consists of a complex of brain states, not just in an active period. In How Much Do We Sleep in One, it says that young adults sleep for a total of 7 to 8 hours, about half in stage 2 sleep. REM sleeps account for 20% of total sleep. The typical night of an adult human's sleep shows repeating cycles about 90 to 110 minutes long, recurring 4 or 5 times a night. Cycles early in the night are characterized by greater amounts of stage 3 SWS, and the latter half of the night has less stage 3 sleep. REM sleep is typically more prominent in the later cycles of sleep. First REM period is the shortest, and the last REM period may last up to 40 minutes. A brief arousal occasionally occurs immediately after a REM period, and the sleeper may shift posture at this time. The sleep cycle of 90 to 110 minutes has been viewed as reflecting a basic ultradian rest activity cycle. Cycles of similar duration occur during waking periods, such as the cycles of daydreaming. At puberty, the circadian rhythm of sleep shifts in most people, so they get up later in the day. A high school shifted their start time from 7:15 to 8:40 and noted improved student attendance and enrollment with reduced depression and sleeping in class. In We Do Our Most Vivid Dreaming During REM Sleep, it says that dreams occur in other stages, including REM. REM sleep dreams are characterized by visual imagery, whereas dreams during NREM sleep are more of a thinking type. A nightmare is a long, frightening dream that awakens the sleeper from REM sleep. Many medications make nightmares more frequent, and at least 25% of college students report having one or more nightmares per month. A night terror is a sudden arousal from stage 3 slow wave sleep that is marked by intense fear and autonomic activation. The dreamer does not remember the dream, but can remember a sense of crushing feeling on the chest as though being suffocated, and it seems to have a genetic component. And different species provide clues about the evolution of sleep. It says many invertebrates have clear periods of behavioral quiescence that include heightened arousal thresholds and distinctive postures, and this is becoming accepted as sleep. Sleep is an ancient adaptation. And REM sleep is evolved in some vertebrates. It says that REM sleep is not quite as ancient as NREM sleep. Nearly all mammals display both REM sleep and NREM. Only birds display clear signs of both SWS and REM sleep. This suggests that either REM sleep was present in an ancestor common to birds and mammals, or that REM evolved independently in mammals and birds. Dolphins don't display REM sleep because this development would be incompatible with the deep relaxation of muscles during REM sleep, since they have to come up to the water to breathe. This is also unilateral sleep. Only one side of the dolphin's brain engages in SWS at a time. Birds also display unilateral sleep, one hemisphere sleeping while the other looks out for predators. Unilateral sleep while gliding may also enable birds to fly long distances without stopping. In humans, the left hemisphere displays less slow wave activity than the right during the first night in a sleep lab. This suggests that the side of the brain remains more vigilant in this unfamiliar locale. The second night in the lab, when people usually sleep better, sleep depth is an equivalent between the hemispheres. In our sleep patterns change across lifespan, it says how much sleep and what kind of sleep we get changes across our lifetime and are most evident during early development. In mammals sleep more during infancy than in adulthood. It says it takes several weeks in an infant to establish a clear cycle of waking and sleeping. A 24-hour rhythm is usually clear by 16 weeks of age. Infant sleep is characterized by shorter sleep cycles than those of adults. This might be because of their immaturity of the brain, and sleep cycles in premature infants are even shorter than in full-term babies. Infant mammals have a large percentage of REM sleep. For example, 50% of sleep in the first 2 weeks of life in humans is REM sleep, even more prominent in premature infants, totaling 80% of total sleep. Human infants can move directly from an awake state to REM sleep for the first few months of life. REM sleep of infants includes active including muscle twitching, smiles, vocalizations, and grimaces. REM sleep early in life suggests that this state provides stimulation that is essential to maturation of the nervous system. Maybe sensory feedback from those twitches guides synaptic development in the brain. Killer whales and bottlenose dolphins appear to spend little or no time sleeping for the first part of their life, probably because they have to come to the surface often to breathe. The conclusion is that REM sleep does not have a crucial role in mammalian infants, or dolphin and whale infants have found a different way to fill that need. In most people sleep less as they age. It says that as you get older, the total amount of sleep you receive declines while the number of awakenings increases. Lack of sleep or insomnia is a common complaint of the elderly. This can lead to deficits in cognitive function. The most dramatic progressive decline in humans and other mammals is during stage 3 sleep. People at age 60 spend only about half as much time in stage 3 than they did at age 20. By age 90, stage 3 sleep has disappeared. This decline in stage 3 sleep with age may be related to diminished cognitive capabilities, since an especially marked reduction of stage 3 characterizes the sleep of people who suffer with senile dementia. Growth hormone is secreted primarily during stage 3 sleep, so perhaps the loss of growth hormone from disrupted sleep in the elderly leads to cognitive deficits. Many elderly people have sleep dissatisfaction, which means they fall asleep easily but cannot stay asleep. Attitude may be important for the experience of sleep loss in the elderly. Objective measures of sleep suggest that elderly people who complain of poor sleep may actually sleep more than those who are satisfied with their sleep.